Hello and welcome everyone. I'm Peter Robinson and this is the Ethereum Engineering Group meetup. Today I'm going to give a talk on security domain separation and cryptography. So let me share my screen. There we go, share. Okay, and people can see my slides, hopefully. Yep, cool, thank you. And I'll get rid of that bit at the bottom because that's not going to help anyone. Okay, so I'm going to talk about what are security domains and try and get a common understanding of what that's all about, and then talk about what can happen if you start mixing these security domains up, and then talk through, well, is this actually a real problem, and then talk through what you can do to do security domain separation and an implementation that you could use, and then talk about what else you could do if you really want to, if you're really protecting a lot of valuable information. So the ASD, so Australian Signals Directorate, the Cybersecurity Centre, they talk about security domains with this definition. And so essentially a collection of systems that are operating under a consistent security policy. So you can imagine, you're going to have a stovepipe of information and it's going to be a security domain. And so you're trying to have the handling of that type of information consistent across the domain. And so that's what is the common definition. And it's really where the term comes from, though I dare say that the term's been around for decades. And in this talk and in the cryptography world, I think of it's more, you can just boil it down to information, where information could be data or cryptographic keys that has a common security level and use. So say keys and data that are all associated with the same thing and at the same security level. And so when I think of this, I'm thinking that, you've got data, that's publicly available, for instance, and then maybe you've got cryptographic keys, so Ethereum private keys or a web server private key, or maybe some symmetric key that's used for bulk encryption, and maybe a variety of other keys. And even within that data, I'm not just talking about, say, plain text, ordinary plain text publicly available data. I'm talking about, say, random identifiers, say initialization vectors that are used as part of symmetric ciphers, salts, so values that are used to differentiate when you're doing, say, password hardening, or maybe cryptographic nonces. So essentially values that are hopefully random, but once they're created, they then become public. So different types of information, essentially public information and private information. And so that's what security domains are. So what happens though if you were to mix them up? And so, you can imagine a lot of people create their software in this sort of way, where you have some, like a PRNG, so a pseudo random number generator, which is also sometimes you might hear of it called a DRBG, so a deterministic random bit generator, really trying to hammer home that it's an algorithm, it's deterministic, and and the input to it is entropy. And so entropy is uncertainty. It's it's pure random information. And the idea is you put the entropy into the PRNG, and then you can produce pseudo random values. So values that look a bit random and are hopefully hard for people to attack. And so often people produce public information directly from the PRNG, and then they might feed it into a key generator of some sort, say a key pair generator or just a plain key transformer to create, say, a symmetric key, or maybe key pairs for, say, an Ethereum private key or a web server key or something like that. And so people will often use this sort of mechanism. And, you can think of it, you've got, an algorithm, 2 algorithms there, and they're just going to pop out stuff based on that entropy that's coming in. And so I'm going to pose a question to people. Is this sequence of bits, of bytes, is it random? So what are people's thoughts?
It looks quite random.
But yeah, it could be random. It depends. If you add the suffix, for instance, randomness is usually defined as a limit of something. That every values appear at the same frequency and so on. So, does it make sense to define randomness in a finite number of values? So you're muted, Peter, and I would like to know your answer.
Yes, you would. Yeah, thank you for pointing out my mutedness. And so I think if you did a frequency analysis of this, in fact, if you did pretty much any test of this, and even if it was a really long sequence, it would pass all those randomness tests. But looking at it, if we were to split it up into 256-bit blocks, that is just the concatenation of doing SHA-256 of numbers 0 to 4. So it looks random at the output, but it's not random at all, really. If you can work out the input, or if you knew that this was the algorithm, so if you had access to the source code and you knew that the input value at the start to the starting point value is 0, and it's just increments, then you could easily have all the possible outputs. And that would then certainly mean if you could see, say, the 3rd value, you could guess what the 4th and 5th value would be.
So Peter, I have a question. If you were to shift it, rotate it or shift it by a few bits, it would still not be random because the algorithm could unshift it and decode it again, right?
Exactly. And the thing to think about is, especially in this era of open source software, but even if it's closed source, even if you've got closed source software is just software that's waiting to become open sourced, either by an attacker or by the company suddenly deciding they're going to open source the software. So yeah, so just because you've got closed source, you shouldn't, if it's just an algorithm, then, and you know that it's going to start at 0, it's not going to be random and it's going to be attackable. And as I was indicating, so if you could observe, say, what the output of SHA-2 and say, see that, this is the value you're seeing, then you could speculate that, you could know that that was going to be the 3rd value. And in fact, in this one, you can even take the PRNG and wind it backwards because you know what the previous outputs are as well. So this very, very simplistic PRNG would have problems of being able to wind it forwards and backwards. But then here's another one to think about. So imagine rather than just always starting at 0, you have a very large, say 256-bit value that you start with. So you essentially randomly choose from a 256-bit field, the starting value, and then you just add 1 to it. So what about, what are its security properties? And what do people think of it, the security properties of this?
So I can still guess could take a long time, but I could still guess the first value.
You could probably. So what I would say with this is that you can probably create a rainbow table up to say 60 bits or maybe 80 bits even at a pinch, you know. I mean, I'm talking about a state-based actor who've got infinite money, but 256 bits is definitely too big. Saying that, what you could do if you're this state-based actor is, rather than having sequential values, you could sort of have a lot of values that are across the number field and try and pick it out. Then I think you'd still be able to stretch, but yes, it would not be secure because you wouldn't be sure if an attacker could then wind it forwards and backwards. So but it does add, even just by changing this entropy going in, you've added a significant hurdle to the attacker. And that's really what I wanted to show by this. So what happens if the PRNG algorithm or the implementation is compromised by the attacker in this scenario? And you know what's going to happen is that if you can see stuff that's happening with that public data, if you see some public data, then you're going to be able to infer things about the secret data, so the keys. And similarly, you could compromise the entropy. So rather than the actual PRNG algorithm or the implementation of the algorithm, you could say reduce the number range. So you know how the first version of that very simple PRNG, it always had 0 as the starting point. And then I said, well, let's have a 256-bit random value that you put in at the start. If, as an attacker, you could force the actual possible values that you could come up with when you're generating your random starting point to only be 2 to the 10 or 2 to the 20 or even 2 to the 60, you've suddenly made working out what the possible pseudo-random values are much easier, and hence you could infer the secret values from the public values. And so as an example, so think about this, say you generate a transaction ID and then you generate a cryptographic key. So, you know, the transaction ID is going to become public, whereas the cryptographic key is obviously secret. And so if the attacker has access to the source code, and you know they can compromise that PRNG, so it's not a strong PRNG anymore, which could be just by compromising the entropy, then they'll see that transaction ID, and then they'll use that value to infer what the cryptographic key could be. And then they can then say decrypt data that's been encrypted with the key to verify they've got the right key. And then they can start encrypting or encrypting data, or maybe they're signing data using the key. As another example, so say the PRNG was slightly harder, you know, and you were generating the secret and then generating the public value, generating the secret, then generate the public value. And so assuming that you can't wind the PRNG backwards, you can only wind forwards, you're still going to have a problem, because you could take the value number 2, so the initialization vector, and then use it to work out the symmetric key. And so the big thing always here is you've got access, the attacker has the source code. And when the attacker's got the source code, they can look at in what order do things happen in the source code, and hence, if they've got that IV, what is the next secret value that gets created? And it's not just public and secret. You can imagine that you could have different types of secrets getting created, say a private key and a symmetric key. And say the private key, say, was on a web server, and maybe that private key isn't well secured. An attacker is able to come in and then obtain that private key. So if they know that then there's some symmetric key that is then generated after that private key, now that they have access to that private key, they can then infer the value of that symmetric key and then decrypt the data used by that symmetric key. So you can see that you've got to you can have cross-contamination even between secret areas, secret domains. So, that's all well and good, but is entropy or PRNG compromise actually a thing? Is it real? And the answer to that is, without a shadow of a doubt, yes, it's a thing. So the article off to the left there is Schneier talking about Debian Linux. So back in about 2008 timeframe, it was discovered that someone had fixed a Valgrind bug in Debian Linux, which was saying, hey, we're accessing this uninitialized area of memory. So they, of course, zeroized that area of memory. And the reason why that area of memory was being accessed without it being zeroized was it was gathering entropy. So the idea is the application would start up, or the operating system would start up, and a way of gathering entropy was to access those bytes that hadn't been initialized to anything. So they should be sort of random. So by zeroizing those bytes, they essentially reduced the amount of entropy available in Linux. On Debian Linux back then. The dual ECDRBG is another really interesting one. So it was an algorithm for generating random numbers that was recommended by NIST even, and in a NIST standard. And the speculation is that, so it essentially uses two elliptic curve scalar multipliers in it. And one is based on the base point, P, and the other one is based on a point called Q. And Q should have been generated at random, but no one ever came up with the proof that it was. And so you can cryptographically prove it was generated at random. So the speculation is that a large US government organization, which could have been the NSA, actually had the private key. And so essentially, using that private key, you could work out or infer future values based on past values, but only if you had the private key. So obviously that was one, a massive intrusion, but two, a real concern, because if a baddie or someone were to break into the NSA somehow or other, get access to that private key and then publish it, then anything that had been using that dual ECDRBG would be essentially compromised, which was deemed really bad. There have been depletion bugs related to operating systems starting up and lots of PRNGs drawing down on the entropy pool. And so there's one article there from 2010, there's another one from 2022. I think it's a common and ongoing theme. Then also, if you look at the bottom left there, we've got random.seed date time now microseconds. And so what that is doing is it's putting in something that's sort of, it's random, but if you know when that seeding happens, even down to the nearest hour or even day or even month, the number of space of that seed is really small, and so you could try all the possible values then to work out, what the random output's likely to be. So PRNG compromise and entropy compromise is a thing. And so how could PRNG compromise really happen? So you could have a poorly designed PRNG, and so often people home bake their own PRNG algorithm, and that's generally a bad thing. You could have a poorly implemented algorithm, and the thing about PRNGs is it's really hard to work out when you've got a bug in one, because the output looks random. So how do you test it? You could have one with a backdoor in it, like the dual ECDRBG. As well, you could have the algorithm of the PRNG swapped out. So, so we've said don't make your own PRNG. So you're going to use a library, and you're relying on that library giving you the right one. Also, you're relying on, say, if there's a default PRNG, that default doesn't suddenly get changed to something that's not very good. And so you're suddenly now looking at the pull requests going into the library that you're using to, hoping that they're not compromising the library. Another issue, of course, is that if the internal state of the PRNG is observable by an attacker, so if they can snapshot the memory of the running computer or say virtual machine, then they could then have access to that internal state and then predict future values. And in fact, this is definitely a real thing where you've got a VM, it's just about to say generate some secret values, and you clone the VM, and then the PRNG on the second VM can then be used to work out what the secret values were on the first VM. So that's definitely a thing. Entropy compromise is also definitely a thing as well. So you can be in limited entropy environments like IoT devices or virtual machines. You can have entropy starvation where you have lots and lots of processes all trying to get entropy at the same time. You can have poorly designed entropy pool management. So rather than it adding more entropy, you essentially set it or overwrite the existing entropy. And you can have poor entropy management and gathering. And also maybe the attacker can observe the entropy that you're using. And so this is obviously particularly a problem on virtual machines. So, and so I think I've pretty much been through this, but, like if an attacker can compromise the amount of entropy, then, you can work through all the possible values of that entropy to work out the possible random values that are going to be produced. Yeah, so one thing to think about, though, is that in this value chain here, if you can add one extra bit of uncertainty into the system, then you're doubling the search space of the attacker. And so to think about this, so say an attacker, when they're running the entropy through the system, say if they have to have, I used to have, like nuclear power stations or something like that, but I thought we should be a bit green these days. And so we've got a solar powered power station running to try and produce enough energy to try and attack, based on 80 bits of entropy. So if you could have 81 bits of entropy, then chances are the attacker is going to need twice as much infrastructure. And if you can go to 82 bits of entropy, then it's 4 times as much infrastructure. So each extra bit of entropy that you can add to a system is going to help you massively. And so that's something worth considering when you're thinking about that value chain of entropy to PRNG. So security domain separation. So what can we actually do about all of this? So this sort of scheme where you've got entropy going into a PRNG, going into a key generator and generating everything is actually really bad, because there is the possibility that the data, the publicly available information, can be used to compromise the private information. You could have separate entropy, separate PRNGs for everything, which would be great. But you might find that's a bit unwieldy. And so maybe as a minimum, what you could do is just have public random values and private random values, and just limit yourself to 2 security domains. The other good thing about this is you only got 2 lots of entropy that you're trying to gather at the start. And so that sort of limits the amount of entropy you're having to draw out of the system. So how do you actually implement this? Well, there is a saying that you shouldn't roll your own crypto. And so here, as the person is saying, the standard advice is don't. And the other thing right at the bottom of the circle here is it's very easy to mess it up in non-obvious ways. So it can appear to work, can pass every test, but it still can be broken. So yeah, there are dragons here. So that's why you should use, as a starting point, a good PRNG algorithm. And so Yeah, so, all right, so we've got a few people who are going to look at the recording because they've got to go off to do things. Yep, so use a good PRNG algorithm. That's a starting point. And use a good implementation that's well maintained. So it's easy to, you know, like there might be multiple implementations out there, but using one that's in a library that's well maintained is a really good start. Use more than one entropy source. So the operating system will give you some entropy, but the application can supply entropy as well. And so you can add seed and have it mixed in with the PRNG information. And so what you could do for this application entropy is you could say there's, on some CPUs, there's something called RD-RAND, which is an instruction which gives you a random number. And you know, you should be able to trust that as a random number, but that's not available everywhere. You could combine that with the nanotime. So nanotime is a nanosecond counter that's available on many CPUs these days, which just counts up in nanoseconds. And so if you at any time just grab that, then that'll give you a good idea of what the current time is. You can also see what the next available memory location is in your running code. And so those values should be pretty quick to gather, and they're going to offer at least a couple of bits of uncertainty in the eyes of the attacker. But there are standards written on how to gather entropy, so have a read of them. And what's useful to do as well is, so before you're creating any important secret, you add a bit of quick entropy. So you gather this quick entropy and then you add it to the PRNG to make it harder for attackers to understand what the future value is. And so remember that each extra bit of entropy that you add doubles the effort of the attacker. Another thing that you should do is use personalization strings. And so the idea here is to make sure that each instance of a PRNG, even if it has the same entropy going in, generates different numbers going out. And so you try and have information that localizes the PRNG to the computer you're using. So say the computer name, username, number of CPUs available, the available memory, MAC addresses, IP addresses, and as well, you have a string which really identifies, right, it's this application, this module within the application, this usage. So maybe it's a wallet underscore public or something like that. And that's sort of really providing a name to the actual application, because you know, you can imagine there might be many applications running and they're all going to have the same MAC address and all that. But if they have a different application name and usage, then they're going to end up coming up with different numbers. And another thing to consider is if you've got a lot of PRNGs, so that you don't have that entropy depletion, you can chain PRNGs together and have a seeder PRNG, which provides entropy to other PRNGs. So you could have this sort of system where you have that seeder PRNG using the system entropy, and then its random output is used as entropy for the other PRNGs. And in that way, you don't have the system entropy depletion. So putting it all together, what it could look like is something like this, where you have your personalization string, which I'm shortening it to just public, but obviously you need all that other information. And then you've got, say, personalization string private, and then you're feeding system entropy in to two PRNGs. And you're also, each time you request a new piece of information, like a key, generate a key or generate some data, you do a quick reseed of the PRNG. So then even if the whole system is snapshotted, you'll still end up with different values. So it'll be hard to predict. Yeah. And you'll be able to find the recording on YouTube in the Ethereum Engineering Group Meetup YouTube channel. So I've said all of that, but what else could you do? You know, beyond this sort of relatively straightforward system that I think any application should consider. Say if I've got $1 billion of my own money, and I really want to protect it, and I'm really hyper paranoid. What could I do? You could do something that looks a bit like this as a starting point. So this is a single block. And so this is a PRNG. This is rolling your own crypto a little bit, but not really. So you come up with the initial state of your PRNG by combining system entropy and that quick entropy, and you're putting that in. And then whenever the output of, when you need to create output, you do a SHA-3 to 56 between the quick entropy and the internal state. And so that's acting as a compression function for creating the output. And each time you ask for a new value, you update the internal state. And what you do is you've got a counter, which is a simple accumulator, and you combine that with your quick entropy and then SHA-3 it with the current internal state to give you the new state. So keep that in mind as a simple PRNG block that you're going to have in the overall diagram. But the idea is you can implement this in your own application. The big thing to think about is that with SHA-3 to 56 or any message digest algorithm, the cryptographic library cannot fiddle with it, because if it changes the hash function, then the hash function will no longer work properly. It won't hash values correctly to the correct value. So hash functions have to work. There's no way of really compromising them. And so what you can do overall, if you're super paranoid, is you've got you have two cryptographic libraries, so two completely separate implementations, and you use two separate hash functions. So say you use hash DRBG and CTR DRBG. So CTR DRBG is based on AES algorithm, whereas hash DRBG is based on a hashing algorithm. And so the idea is that you feed in your personalization strings and your system entropy into these two PRNGs. And then you've also got your simple PRNG block. And the idea is that you combine all three of these. So if one of those PRNG algorithms ends up being weaker than everyone thought, or the implementation in one of those cryptographic libraries turns out to not be working correctly, you'll help to cancel that out. And by having your own mini simplistic PRNG that you're combining in, it's providing a bit of extra safety as well. So even if there's some problem with all of this stuff coming into your application, you've still got some uncertainty going in. And so if you're, say, message digesting these 3 lots of 256 bits and you bang out 512 bits. So that should provide a fair bit of security for you. So in summary, an attacker might be able to launch some sort of attack to infer information about one security domain from another security domain. So, you do need to be aware of this sort of thing. And so, especially if you're generating, say, identifiers or some other public information, and you're generating secret values like, say, Ethereum private keys or some other cryptographic keys, then you really need to be cognizant of this. And so using those separate security domains and separating it out, having separate PRNGs, certainly helps prevent these sorts of attacks. And doing some little bit of quick seeding, not spending lots of CPU time, but just a quick bit of CPU time, and adding a few more bits of entropy into your PRNG can certainly help, certainly raises the bar significantly to attackers. So before I answer any questions, if there are any, you can see that there are a stack of talks coming up. In fact, we've got one a week or so for the next month. So lots of very interesting talks. We've got one on DAOs by Aaron. I'm delivering a talk on Solidity security after that. And then Horacio is going to talk about the Ethereum reference test system. Ermias is going to talk about the security of cross-chain transactions and look at it from an overall perspective, a holistic perspective. Paul Ashley is going to talk about DIDs. We've got Jacob Illum, who's the chief scientist from Chain Analysis, who's going to give a talk. We've got Lachlan Robb talking about the socio-legal aspects of blockchain. So what the intersection of those two. And the last one is from Ming-Fan Kui, which is a DeFi-enabled data marketplace. Okay, and so I'm not sure, I'm going to learn more about that before we get to it. But so we've got a whole stack of talks coming up. And there are the socials, including that YouTube link. Yeah, but are there any questions?
Thanks for a great talk, Peter. But this is not a question as much as an observation on your list of talks coming up. And I think there seems to be a mix-up between Tuesdays and Wednesdays, because I thought the first one show there is, it's just because I know my daughter's birthday is on, is on a Tuesday and it's the 9th, and I think, so I think Aaron's is the day after, August the 3rd, as opposed to August the 2nd you've got up.
Oh, yeah, so let's have a look. Maybe I do have the wrong dates. I know one of them is a Tuesday, because for those who don't live in Brisbane, we have a public holiday called Echo Wednesday. Oh. Yes, so Aaron's is the 3rd. All right, everyone, ignore that. Ignore the August the 2nd and think of it as August the 3rd. Okay. But yeah, the Tuesday, August 9th is correct, because that's Wednesday. Okay. Yep. And so we're going on Tuesday.
No worries.
Yeah. All right. Thank you, Sandra. Are there any other thoughts or questions about all of that? And does, Ali has his or her hand up, their hand up. So please.
Hi.
Yeah.
Sure, Peter, thank you for this information. It was a fantastic talk. I am working in this space of, I'm essentially trying to create a data backpack. And one of the biggest challenges I have is, how do you perform key management on behalf for the user while they own the keys? So the easiest form to do that, of course, is just through them owning MetaMask and using encrypt, decrypt MetaMask. I've seen your previous videos on that, and essentially you were pointing out a major flaw in that logic, where you shouldn't use one set of private keys to control large sets of data. So I wanted to ask you, do you know of any way of where I can have the user still own the keys, but at the same time achieve what I want, which is them to encrypt multiple sets of data?
Yeah, that's a complicated one. Yeah, trying to have the user control many keys and lots of data. I know there are things happening in MetaMask, but yeah, it's a complicated one, because I mean, as much as anything else, how does the user know which of the many keys they might have to use? So do you then have some sort of, I mean, how it's often done in large systems is you might have a symmetric key that has been encrypted with a maybe an asymmetric key or maybe another symmetric key, and that encrypted symmetric key is kept with the data. And then the idea is that, so then your bulk data is, like encrypted using the symmetric key. And so you can sort of incrementally, like you decrypt the symmetric key and then decrypt all the data. So then you don't have maybe quite so many keys, but then you are potentially using your key for encryption as well as signing, which is a bit of a no-no. So you're better off having a separate key pair for that.
Thank you for the response.
Yeah. Are there any other questions? All right, I think we've done the 30-second rule. I don't know. I think someone said you're supposed to wait for an hour, rather not an hour. Wait for a minute. Wait for a minute. If you waited for an hour, everyone would die. David said, "Come on, we're not going to wait on the call for another hour waiting for questions." Yeah. All right. So look, great to have everyone along, and see you in about a week's time. Talk later.
Thank you,
Bye.
Peter. Thank you.
Thanks, Peter.
Thank you.
Thanks,
Awesome.
Peter.
Okay.
Take care.
Thank you, Peter. Bye.
Thank you so much.